In this lesson, you will learn about traffic and session monitoring. After completing this lesson, you should have the practical skills and knowledge required to interpret the information in Session Table, capture traffic using the built-in sniffer, analyze the output of the debug flow, configure and troubleshoot session helpers, and configure and troubleshoot the SIP application layer gateway. In this section, you will learn about session table entries. The FortiGate session table contains detailed information about every IP connection that crosses or terminates at FortiGate. The command get system session status displays the total number of sessions in the active VDOM. The command get system session list provides a brief summary of each session. This command lists one session on each line and includes information such as protocol, source IP address, destination IP address, and port. You can use the grep utility with this command to list only the sessions for a specific IP address. To display detailed information about sessions, use the command diagnose sys session list. It is recommended that you set the session filter first, as an unfiltered output displays all the details about all the existing sessions. For high-end devices, a list of all existing sessions could be in the thousands or even millions. You can filter the output by policy ID, source IP address, source port, destination IP address, and destination port. Some configuration changes, such as security profile or session helper changes, apply only to new sessions. In the case of those changes, existing sessions keep using the old configuration until they expire or are terminated. This is important to remember when troubleshooting problems. After a security profile change, you should clear any sessions related to that change and generate new ones. Use the command diagnose sys session clear to remove all sessions that match the session filter. You must be very careful with this command because it can, potentially, clear all the existing sessions if no filter has been set. Before you remove all sessions, use the command diagnose sys session filter to check the filters. This slide shows a sample of the output contained in the FortiGate session table. From left to right and from top to bottom, the following information is highlighted: IP protocol number and the protocol state. This value is covered in this lesson. How long for the session to expire if there is no more traffic. Traffic shaping counters, session flags, received and transmitted packet and byte counters. If the unit is doing NAT, this portion shows the type of NAT, source or destination, for each traffic direction, and the NAT IP address, source MAC address of the packet, ID number of the matching policy, and counters for hardware acceleration. The protocol state in the session table is a 2-digit number. For TCP, the first number is related to the client-side state and is different than 0 when the session is being handled by a FortiGate proxy. For example, when the FortiGate is doing proxy-based inspection. The second digit is the server-side state and is used to identify the status of the TCP session. This table and the flow graph correlate the second digit value with the different TCP session states. For example, when the FortiGate receives the SYN packet, the second digit is 2. It goes to 3 when the SYN ACK is received. After the three-way handshake, the state value changes to 1. When a session is closed by both sides, FortiGate keeps it in the session table for a few seconds more to allow any out-of-order packet that might arrive after the FIN-ACK packet. This is the state value 5. For UDP, the session state can only have two values, 0, 0 when traffic is only one way, and 0, 1 when there is traffic two ways. For ICMP, the protocol state is always 0, 0. This table contains the meaning of the most important session flags. For example, the log flag indicates that the session is being logged. The local flag indicates that the session either originated from the FortiGate or is terminating in the FortiGate. Let's take a look at the dirty and may dirty flags. When FortiGate receives the first packet for a new session, it evaluates whether the traffic should or should not be allowed, based on firewall policies. As long as there are no changes in the firewall policy configuration, this evaluation is done only on the first session packet. If the traffic is allowed by firewall policy, FortiGate creates a session and flags the session as may dirty. After that, if there is a change in the firewall policy configuration, all the existing sessions with the may dirty flag are also flagged as dirty. This indicates to FortiGate that it needs to reevaluate the next session packet to determine if the session must be blocked. If the session is still allowed, the dirty flag is removed, but the may dirty flag is kept. If the session must be blocked, it is flagged as block and remains in the session table until it expires. Any packet matching a session with the block flag is dropped. In this section, you will learn about two useful troubleshooting tools, the built-in sniffer and the debug flow. Let's review the built-in sniffer. When you enable this tool, you can choose from 6 verbosity levels. The table shows what information is displayed in each level. We usually use level 4 to check how the traffic is flowing and if FortiGate is not dropping packets. We also use level 3 or 6 to convert the output to PCAP format, which can later be analyzed with a tool such as Wireshark. To sniffer traffic in all interfaces, use the keyword any as the interface name. Stop the sniffer by pressing Ctrl-C and check for dropped packets. If there were dropped packets during the sniffer, it means that not all the traffic that matched the sniffer filter could be captured. So, you might need to capture the traffic again, using a stricter filter or with a reduced amount of traffic to capture. If you don't specify an option for the timestamp, the debug shows the time in seconds since it started running. As explained earlier in the lesson, you can prepend the local system time to easily correlate a packet with another recorded event. Another useful FortiGate troubleshooting tool is the debug flow. The debug flow is also called internal sniffer because it works similarly to the built-in sniffer, but the output shows step by step and with details what the kernel is doing with each packet. This is a sample of a debug flow output. In this example, the debug flow has captured the 3 packets of a TCP three-way handshake. The output for the send packet shows when the kernel creates a new session with its session ID, finds the route to the destination, and applies NAT. It also shows the ID of the policy that matches this traffic. The output of the SYN-ACK and ACK packets shows the session ID and NAT information. This tool is useful for many troubleshooting cases, such as when you need to understand why a packet is taking a specific route, or when a specific NAT IP address is being applied. The debug flow can also help you determine why FortiGate is dropping packets. In those cases, the debug flow usually shows an error message explaining why a packet was dropped. This slide shows 3 messages that you commonly see in debug flow output when FortiGate is dropping packets. 1. Denied by forward policy check. Indicates that either no firewall policy allows the traffic, or that a disclaimer has not been accepted yet. 2. Denied by endpoint IP filter check. Indicates that the IP address has been quarantined by the DLP inspection. And 3. Exceeded shaper limit drop. Indicates that the packet was dropped due to a traffic shaper that has exceeded one of its thresholds. This slide shows 2 more common debug flow error messages. The first error message indicates that the packet failed the reverse path forwarding check. The second error message usually indicates one of the following. The packet is destined to a FortiGate IP address, for example, management traffic, but the service is not enabled. The service is using a different port. The source IP address is not included in the trusted list, or the packet matches a local in policy with the action deny. The packet is destined to a device on the other side of FortiGate, but a virtual IP or IP pool is wrongly using the IP address. In this case, check your virtual IP or IP pool configuration. Not all the sessions are created by traffic matching existing firewall policies. In this section, we will look at how FortiGate can create sessions for traffic that is expected to come, but hasn't arrived yet. This is part of what session helpers and the application layer gateway do. To understand what a session helper does, let's look at an example of a network protocol that might have problems when a network device is doing NAT. This example shows FTP protocol working in active mode. Any FTP file transfer is composed of 2 TCP sessions, one for the control channel and one for data transfer. The control channel is always initiated from the client to the server and is used to send the FTP commands. The FTP commands allow the client to move through the server folder, specify the type of file transfer, and initiate the data channel for uploading or downloading a file. FTP has 2 modes, active and passive. The mode determines who initiates the data channel. In passive mode, the data channel is initiated by the client. In active mode, the client sends the port command through the control channel. The command includes the client IP address and the TCP port for the incoming data channel. Then, the server initiates the TCP session to the IP address and port number specified by the port command. Active FTP won't work if the control channel crosses a network device doing NAT that does not have a session helper. In this example, an FTP client is connecting to an active mode FTP server. There is a router in the middle doing NAT of the client IP address 10.0.1.10 to the NAT IP address 10.200.1.1. After the control channel is up, the client sends the port command with its IP address 10.0.1.10 as the destination for the data channel. When the FTP packet crosses the router, the source IP address in the IP header is changed from 10.0.1.10 to 10.200.1.1. However, the IP address in the FTP port command is not translated to 10.200.1.1. Once the server receives that FTP command, it tries to bring up the TCP session for the data channel. It sends the SYN packet to the IP address 10.0.1.10. This address is probably not routable, as it is a private IP behind a device doing NAT. This file transfer fails. The FTP session helper fixes this problem. Let's replace the router with FortiGate. This is what the FortiGate session helper does. When the packet with the FTP port command arrives at FortiGate, FortiGate not only translates the source IP address in the IP header, the session helper also translates the IP address inside the FTP port command. If the source port is also translated in the TCP header, the session helper also does the same in the port command. Another important function of the session helper is to temporarily create an expected session, or pinhole, for the data channel connection that will come from the server. That means that the administrator does not need to manually create firewall policies to allow these incoming TCP sessions, which use random TCP port numbers. The session helper automatically creates the session and opens the door for the incoming connection. After that, the server connects the data channel to the right IP address, 10.200.1.1. That incoming TCP connection is allowed by the expected session previously created by the session helper, even when there is no firewall policy allowing it. This slide shows a packet capture of the previous FTP traffic before the port command reaches FortiGate. We see the original client IP address, 10.0.1.10. This slide shows another packet capture, this time after the port command crosses FortiGate. The session helper has translated the IP address inside the port command to 10.200.1.1. SIP is another protocol that requires a session helper in a NAT environment. Similar to FTP, SIP uses control channels and data channels. In SIP, 4 data channels, 2 for each traffic direction, are required for each call. In this slide, there are 2 SIP phones with the IP addresses 10.0.1.10 and 172.168.100.205. Additionally, a FortiGate is doing NAT on 10.0.1.10 to 66.171.121.44. Once the control channel is up, a SIP phone sends an invite packet with its IP address and port numbers for 2 of the 4 data channels. The FortiGate session helper creates 2 expected sessions and translates the IP address inside the invite packet to 66.171.121.44. The remote phone sends an OK packet to the right destination IP address, 66.171.121.44. The packets include the IP address and ports for the other 2 data channels. The session helper creates 2 more expected sessions, this time using the information coming in the OK packet. After that, the 4 data channels can be connected through the 4 expected sessions. Firewall policies are not needed to allow this traffic. There is a way to list the expected sessions created by the session helpers. In this example, the diagnose sys session list expectation command lists an expected session to allow traffic from 10.171.121.38 to 10.0.1.10, port TCP 50365. The debug flow shows the name of the session helper, if any, that is inspecting the traffic. In this case, it is the FTP session helper. Also, for traffic that matches an expected session previously created by a session helper, the debug flow shows the message, find an EXP session. There are other protocols that, in some circumstances, also require a session helper. For example, PPTP, H323, and RSH. We can list the active session helpers by typing the command show after the command config system session helper. The output lists the TCP or UDP port numbers that each session helper is listening to. If one of those protocols is using a different port number, you need to change the FortiGate configuration to match it. For SIP traffic inspection, the FortiGate includes a feature smarter and more versatile than the SIP session helper. It is the SIP Application Layer Gateway, SIP ALG. The SIP ALG has all the same functions of the SIP helper, but provides more features. Also, while session helpers run in their kernel, SIP ALG runs as a user space process. FortiGate uses either the SIP helper or the SIP ALG, depending on configuration. The system setting, default VoIP ALG mode, specifies which one is used when no voice over IP profile is applied. If it is set to proxy-based, which is the default, SIP ALG is used. If it is set to kernel helper-based, SIP helper is used. If the SIP traffic matches a firewall policy with a voice over IP profile, SIP ALG is always used, regardless of the default VoIP ALG mode setting. Fortinet recommends the use of SIP ALG. The SIP helper should only be used when the SIP ALG is not working as expected. These are the commands you use to change the ports for the SIP ALG. The SIP ALG supports SIP over UDP, SIP over TCP, and encrypted SSL SIP. The command diagnose sys SIP proxy calls list displays all the active SIP calls. The command diagnose sys SIP proxy calls clear disconnects all the active SIP calls. There are two real-time debugs that display information about SIP traffic. Diagnose debug application IM31 and diagnose debug application SIP with the debug level specified. In this lesson, you learned how to do the following. Interpret the information in session table. Capture traffic using the built-in sniffer. Analyze the output of the debug flow. Configure and troubleshoot session helpers. And configure and troubleshoot the SIP application layer gateway.